Hello everybody, welcome to online lecture number 10. This week we start with a new subject called rates of reaction. But first let's talk about last week. And last week what we learned was that for any chemical reaction, if you have it in equilibrium, that means the reaction is given enough time to reach a equilibrium, then the composition of the reactant mixture is not completely pure products nor completely pure reactants. It's somewhere in between, and this composition is given by the equilibrium constant K that contains the activities of the reactants and products in equilibrium and their corresponding stoichiometric coefficients. So the equilibrium constant tells you about the equilibrium composition of a reactant and product mixture. So we learned that this equilibrium constant is determined by the Gibbs free energy of reaction at standard conditions and the temperature. So this relation, combined with the second law of thermodynamics expressed in terms of Gibbs free energy, led us to this expression where we find that the equilibrium constant K depends on the temperature in a reciprocal way, so an inverse temperature term is there. And now whether the equilibrium constant increases or decreases with increasing temperature depends on the sign of the enthalpy of reaction. So for an endothermic reaction we have a positive delta H. Increasing the temperature increases the equilibrium constant. The equilibrium is shifted to the products. For an exothermic reaction where delta H is negative, increasing the temperature decreases the equilibrium constant. The equilibrium is shifted towards the reactants. So today let's talk about rates of reactions. So maybe you've noticed this. There are some reactions that have a very negative Gibbs free energy of reaction. So they should be spontaneous, or at least their composition in equilibrium should correspond to somewhere near the product. But what we see is they react very slowly. An example is, for instance, sugar in air, right? Glucose. Glucose reacts with oxygen, and it has a quite negative Gibbs free energy of reaction. But you see the sugar, nevertheless, even though it should be spontaneous, it doesn't burst into flames immediately, or it remains as glucose. So this is an example of a really slow reaction. It takes place, but it's very, very slow. The sugar is actually on fire while you look at it, just at a very, very low rate. So why is this? What is the speed of a reaction? How is it determined? So one thing you could think of course, so if you have reactants A and B, for them to react, they must meet, right? So they must collide. So if, for instance, this is a gas, they must bounce into each other and then exchange energy and undergo the reaction. But the question is, how often does that happen? And how often do they collide? And you probably can intuitively say that it may depend on how many of them are there. Like the more A and B's, the higher the chance for collisions to happen. So we can also say it must depend on the concentration of the reactants. So it just increases the chance of encounter. And the rate of collision is actually proportional to the product of the concentrations of reactant A and B. So here's an example. We have a hydroxide that reacts with bromomethane to form methanol and a bromine. So what I plot here is the concentration of the bromine against the time. And you see that the concentration increases, but it reaches a constant value after some time. And see this, the increase at the beginning is very, very strong. It increases very quickly over a certain amount of time. So with this we can define the so-called rate of reaction. And the rate of reaction is actually the slope of this curve. So I draw these tangents here, and their slope is the change of the concentration during a certain time interval divided by this time interval. Right? So mathematically we can express it with this. Delta C, and the I is now here, for instance, the bromine. Delta C bromine, for instance, over delta T. Now to mathematically accurately describe this curve of the increase of the bromine, we have to take the limit. That means we make delta t very, very small. And this can be written as a differential, right? So now the infinitesimal small change of the concentration over an infinitesimal small change of the time. And as we stated before, this rate of reaction, it depends on the probability of collision, and the probability of collision is proportional to the concentrations of the reactants, so the hydroxides and the bromomethanes. So it's proportional. That means we need a proportionality constant, and in this case it's the K value. And this K value is the so-called rate constant, and it has to be experimentally determined. We'll talk more about that later. So Ci, as I said before, that is the concentration of either a reactant or a product. So here it's the product, the concentration of the product, right? Here it's actually the concentration is expressed with these brackets, but in my formulas I use C as the concentration. So now the rate of reaction, so the change of the concentration over time, in this case it's the change of concentration of bromine ions over the time interval. So this is for a product, right? But if you look now at a reactant, it has the opposite curve, the inverse curve. So instead of increasing, the reactant concentration decreases, but it, in this case, decreases equally fast as the product increases. So this means simply it has a negative sign before this differential expression, right? So we can generally say this rate of reaction of the products equals the negative rate of reaction of the reactants. So generally we can write an expression for a reaction equation with the stoichiometric coefficients and define the rate of reaction. So it depends, as we discussed before, on the concentrations, but now we introduce these exponents that are corresponding to the stoichiometric coefficients. And this is a very important definition that you should memorize, because you'll need it more often. So for A, the reactant A, we have an order parameter. It's called the order with respect to A. That's the exponent that is the stoichiometric coefficient. And for B, we have the same thing, just the stoichiometric coefficient of B now. So this has an order of A and an order of B for the two reactants. But for the overall rate of reaction, we have to sum these individual orders to get the overall order of the reaction. So now look at the expression. You can see that the A exponent is used on top of the concentration. So now say if the concentration is mole per liter, but if A would be 2, then now we would get mole per liter to the power 2, right? So now that means that the rate constant K, it has units that convert the unit of this side to a rate of reaction unit, and therefore the unit of K depends on the order, on the overall order of the reaction. So for you to be able to use this expression in order to express the concentration profile that we saw in the graphs before, you need to integrate it. Okay guys, so then let's now integrate this rate equation. And we start, of course, with a simple example. So please, this is going to involve a little bit of mathematics now, but it's not that bad. You should be able to easily follow this. So example 1, A, it just reacts to products, right? There is no B. So you can see the order of this equation, of the rate equation, is just 1, because A has stoichiometric coefficient 1, so this exponent is 1. B is not present, so this whole thing doesn't matter. So the expression, since it's for the products A, we have here the negative rate of reaction, and that equals just the rate constant, K, times Ca with the exponent 1. Right? So now we define that at the beginning of the reaction, at T equals 0, we have a starting concentration of A. And that's called Ca naught. So it could be any numerical value. We just use a formula symbol as a placeholder. So now, in order to integrate this equation, what I have to do, I have to separate the variables. It's quite simple in this case. So dCa and Ca, I bring them on one side. So I just divide by Ca. And dt, I bring on the other side. So I multiply with negative dt. Right? So this is the right-hand side. Good. So now we integrate. So I put my integral sign for this expression and the integral for the right expression. So on the right side, I integrate from time 0 to time t, right? And the k, it can be taken out of the integral because it's a constant. And on the left side, I integrate from the concentration at time 0, Ca naught, to the concentration at time t, Ca. Right? Now I need to solve this integral, and you probably know from your math course, an integral of 1 over x dx gives the ln of x. Right? And it's the same thing here. For an integral of 1 over Ca over dCa gives ln Ca of the upper bound minus ln Ca naught of the lower bound. Right? So the right hand side is more easy to integrate. It's just minus k times t minus 0. And now we can combine these two with this logarithm rule and the kt on the right side. So rearranging for Ca now, I have to put this into the exponent of the Euler number and multiply it with Ca naught. And this is now the equation that models this profile of the concentration of A. Right? So let me calculate it for an example. So here's a little Excel spreadsheet that I prepared. So Ca naught, my starting concentration of A, is 4 mole per liter. Right? And now I would like to compare 3 different K values, 3 different rate constants. So 0.03 per second, 0.06 per second, and 0.2 per second. So this is the slowest and this is the fastest. So here in this table, I plot the time in seconds from 0 to 15 seconds and beyond, that's below here. And here in these 3 columns, I plot this expression. So I just feed the expression here with the K value in the exponent and the time and the starting concentration. So you see at 0 we have 4 mole per liter for all 3, but then after 1 second this is the one with the slowest rate constant, this is the one with the intermediate rate constant, and this is the one with the highest rate constant. So the concentration decreases because the reactant is proceeding, and I plot it here. For the slowest rate constant, it takes the longest time to go down to full product, and for the intermediate and for the fastest, it's very quick. So even for the 0.2 per second, after 20 seconds, I almost have full conversion. So this is a slow reaction, and this is a fast reaction, and this is a reaction of first order. So what you could think now is, what do I do if I have, for instance, measured the concentration of a product or of a reactant over time, and I have a plot of this concentration. I have the data, so I used spectroscopy to measure the concentration. How do I figure out which order does this reaction have, the rate law? And so here's the integral again, and here our expression that we started with after integrating. So what I can now do is I can just add the ln Ca naught to the other side, and then I get this expression. And maybe you see this is a linear equation. So this is one term that's linearly dependent on the time with the slope k, negative k, plus an axis intercept ln Ca naught. So for instance here, this could be data that was measured in a laboratory. Like time was started, someone started the timer, and then the reaction began, and it began at 4.1 mole per liter, and then you take samples and you measure at a certain time always what's the concentration of my reactant A, and then you take the logarithm, the natural logarithm of this number, and plot it against the time. Now you can see here is the plot, here's the time, here's the logarithm plotted against the time, and for this data you see the points that correspond to the ln of the concentrations, they follow a linear line. So meaning, since we plot ln Ca against time, this linear equation is really satisfied. It seems to work. So all we have to do with Excel, for instance, we have to fit this linear slope now with an equation, with a linear regression, to get numbers for the slope, that is the k value, minus 0.0199, and the intercept, ln Ca naught, 1.3. So this is the number up here. So you see, the intercept is the axis distance from 0 to where the linear equation hits the axis, and we get the number 1.35, and from that we get a starting concentration of 4.1 mole per liter, like here. And the slope of this curve is the k value, and we find there is a k of 0.0199. Okay, that was a reaction of first order. So here example number 2. So now we have 2a, and you can already see, because of the stoichiometric coefficient 2, we get now a second order reaction. And again, the same expression for the rate constant. So separating the variables again, now I divide dCA with Ca to the power 2. That gives Ca to the power negative 2 times dCA. And the right hand side times negative dt. And again, integration from Ca naught to Ca, and times 0 to time t. And integration of Ca to the negative 2 gives minus Ca to the negative 1 from Ca naught to Ca. And I can write this now with the bounds of the integral plugged in. Ca to the power negative 1 minus Ca naught to the power negative 1. And this, with the negative sign, converts to this expression, equals minus k times t. So rearranging a little more for Ca gives me this expression, and now I obtain a equation that tells me how should the concentration of the reactant A behave over time t, and this is the rate equation, or the integrated rate equation for a second order reaction. So here we have a little Excel sheet. I plot the concentration of A against the time, and I compare now a first order, which we solved before, to a second order, and you see that the concentration in the first order, it decreases more quickly than in the second order, because in the second order reaction we have the requirement that these two A's, they must collide with each other, and this is less unlikely than what happens in a first order reaction, so it's a little slower. Okay, so you can also think of now, there is a way how to linearize this integrated rate equation to find out whether we have a first or a second order reaction. So this is actually part of the homeworks. So after this you should be able to solve these homework problems, and I think the later ones are a little challenging, especially where you have to also find out what order your reaction has. Okay, next time.